let's start by saying that we have a semicircular bar of charge Q. And let's also establish that the bar is a true semicircle, 1/2 of a circle, and that let's put in here some points of measurement. This is just to help us kind of establish some measures that we can use here. I think that will do. So, although I've drawn the bar kind of thick, let's assume that it's thin relative to its size. So we can again treat it like a length and not a volume. And let's say it has radius capital R. And we're going to bring another charge of charge little q right up to the center. And I'd like to find what the net force is on the little charge. Does that make sense? Any questions about what I'm asking you to find? I think if we look at this, our parameters for our answer will probably need to be those three and any fundamental constants. Now we may need to invent some variables to do this, but I think this is where we're going. Now, in doing a problem like this, I gave you guys a series of things that you may wish to do. You guys remember that from yesterday? To decide how to do this, we're probably going to invent some variables, and it might be more than one. At the end of the day, we want to integrate over a variable that will allow us to sum up the contribution of the force for each part of the bar. So we may invent some variables. Let's understand what can and can't be in our answer. I'm thinking right now, we can have the total charge of the bar in our answer. We can have the radius will be in our answer. And I think the size of each charge will be in our answer, right? I think those will be the things. Coulomb's law is just about the size of the charges and the distances involved. Now the next thing is I want to find a way of breaking up my large distribution of charge into small pieces. And I told you how to do this yesterday, so I think we're going to do it today. Draw a box somewhere. A box that represents a single piece of the charge. I don't know how you might want to do that. I kind of have an R already sitting out there. I was kind of thinking I'd draw the box right there. But you can draw wherever you want. This is your thing. But now, this is where I want to stop talking and let you take over. And by take over, I'll probably go table to table, see what you do. You need to set up the geometry in such a way that we can point at each piece. So what I think you should do here is you should probably get a handle on how does this one portion of the bar affect the small charge at the center. And from there, build an idea of how each of these pieces would be similar and how each of these pieces would be different, and look for symmetry. So I'm going to give you a second, but maybe draw out some things that you could use to point to every single one of the boxes. This is easier than you think, but you've never done it. So now I need you to try it. See what I mean? Try something better. Give me an alignment point, a point of alignment that would work here. How about aligned with R? Oh, yeah. Drawn away from or towards the arc of charge? Okay. Does that seem like a reasonable thing to draw? That gives me an idea. I already have R drawn in there, but the force would be on that particle from that single piece would be in this direction, right? Aligned with the radius. That's not greatly aligned with it, but I'm doing my best. But away from the semicircle of charge. Good so far? Okay. Now that we've done that, that helps, because remember, there's other things here. Now, if I'm trying to figure out the size of the total force on the charge, I understand there are other pieces of charge, right? I mean, I can consider the fact that there's a box over here someplace and a box over here someplace. Each one of these is a different part of the bar. Each one of them is applying a force to the charge. And I have to point at each one of them, figure out how much force that piece applies, and then go on to the next one and add its, and go on to the next one and add its. But my math only allows for one dimension. That's one thing we have to start thinking about. So in doing this problem, we are going to have to break it up into a net force in the x direction and a net force in the y direction. That's something that's coming. So let's establish some directions here. So can we all jump in on the fact that this could be the x direction and this could be the y direction? That all okay?
Yes.
Excellent. So that's helping us out. Is there, going back to Aaron now, any symmetry that you see here? And can you describe what the symmetry will do to this problem? Because that's the important answer.
Oh, then one of either the x or the y will be 0.
I'm hoping that will make it easier, right?
Yeah.
Because if one of these is 0, I only have to focus on one of the dimensions. Do you think one of these net forces will be 0? Which one?
Y.
Okay. Does anybody agree with Aaron that it's very likely that y will be 0? The net force in the y direction will be 0. Okay. I agree too, because as I look, if I were just to consider this charge right here, this piece of charge, it clearly is going to have a force in that direction. And although part of that force is to the right for sure, it looks like the other part of that force is upwards, and it's going to balance, I think, potentially balance the downwards force from my initial charge. Now, this would only be true under certain circumstances. You know, like, for example, it would be true if this dq over here and this dq over there are the same size. Is that possible? Is that likely?
Yes.
Yeah, it's a uniform charged bar. So as long as I make each piece the same size, they will have the same charge. But the other question you have to ask is, are they the same distance away? Because that's how Coulomb's law works. If those two things are true, then it's likely that both of these parts of the force are of equal size, but have some symmetry to them. Meaning, the force that's in this direction and the force that's in this direction are probably the same on the other side. So although the yellow parts add together, making the force in the horizontal direction bigger, the blue parts cancel out. So I think you're right. I think we can say net force in the y direction equals 0. So we've used some exploitable symmetry. We're only going to care about the net force in the x direction. And from looking at this, there might be a trigonometric way to filter out the part of each force in the x direction. All right. So let's start setting up some geometry, a way that we could figure this out. I think, based on what we just said, and if we go ahead and remove some of this excess and get back to just studying the one we started with, we could focus a little bit on just this part. I think it might be in our best interest to maybe have this angle. Does that seem like a reasonable angle to have? Maybe introduce it into our problem, because I think we're going to need it. I think to get the net force in the x direction, we're going to take each piece of force and multiply by the cosine of that angle to get the piece of force in the x direction. I'm just writing it a little different because I'm taking the summation away to talk about just this part of the force. and recognize that I only need from this part of the force the portion of it that's in the x direction, and then I will add all those pieces together. Do you follow why I'm rewriting this a little bit? So if I add them all up, I'm putting the summation symbol down there just to remind you it's a sum. If I add all the parts of the force that push in the x direction, I should get the total force on my particle. Everything good so far? All right. I think this is theta. Would you guys agree with me?
Yes.
Okay. Now, I'm trying to set up my geometry. And yesterday, I'll remind you that one of our problems is that you might have more than one variable that you use. It's in your best interest to try and reduce the number of variables that you use to point to each piece down to the fewest number possible. And in this class, we want that fewest number to be one. One integrating variable if we can. Is there a way for us to do that here? And I think there might be. Isn't every single piece of arc the same distance away?
Yes.
Like, this wasn't true on the bar yesterday. On the bar yesterday, every single piece of the bar was a different distance away. Because the bar was flat, and some of them were close to my dot, and some of them were far away from my dot. But it doesn't matter which piece we choose here. They're all going to be a distance r away from our charge. In fact, in thinking about the future here, where I know there's going to be Coulomb's law introduced here with Q1, Q2, K over, I can go ahead and say every piece of charge is going to be capital R squared away. Doesn't matter which of these pieces I choose, right? So if I want to point to every piece, I could probably start with an angle down here and then choose every angle that takes me all the way around the bar. Now, there's a good reason not to do that, and some of you know why. It's kind of a quirk in mathematics. It's not. It's an issue with dealing with sine and cosine and taking integrals, where you may have a problem with some kind of parity. So whenever you're faced with something like this, that's going to go from like 0 to 180, or from negative 90 to positive 90, or in radians, negative pi over 2 to positive pi over 2, something like that, you have to be careful that you might run into trouble when you take your integral. This is something that you will learn in calculus, and I don't want to spoil it for you too much, but if you can, it's always best to consider if it's symmetrical, maybe start here at 0, go along one side, and then just double your answer. It helps prevent you from getting into a situation in which the trig gives you a 0 on both ends of that. Because that can happen. It's like finding the area for one complete sine function. The area is 0 because half the area is above the axis and the other area is below the axis. Does that really tell you the area, knowing it's 0? Not really. It's not giving you what you need from a sum. So we have to be mindful of the functions that we have here. This won't come up often, but doing something like this is very helpful. So just consider thinking about that in the future, because we're going to have a lot of circular problems. Okay, our next spot is to try and build the size of dq. We want to write the size of dq in something that's about the location of our charge. Now, yesterday, if you'll recall, what we did is we just said that the size of our charge was a certain length, dx. Do you remember that? We're going to do the same thing here. I want you to write the size of the charge in terms of a small length. Please do so. You don't have to do much. Just do the exact same thing we did yesterday. See this.
Number 18, or like the guy next is to 18?
Well, whoever's if somebody's sitting in 18, they have to be the one to answer.
Oh, that's yeah.
If there's nobody sitting in 18, then it's the person closest. Who's 18? Excellent. What do you think we should do here?
we know that the density is equal, so we would set the ratio equal.
Okay?
So the length of this shape is pi r.
The length of the shape is pi r, okay?
Yeah.
So you're talking about the entire shape is pi r. So you're saying we should make, I'm just going to give us some space to work here. Q over pi r equals
dq of d over d of pi r.
d of pi r. No, I need a length, but I just want a piece of the length here. So I don't think pi r will work.
So d of x.
Okay? Now this introduces a new variable. So this may or may not be okay. So let's just, I want to go with this for just a minute. Some of you probably know we're going to have to make a change here, but right now we have two possible integrating variables. We can integrate over dx, or we can integrate over something that has to do with theta. So we either have to write x in terms of theta or theta in terms of x. And right now, dx represents this piece of arc length. Now, just symbology for you guys, just for a few minutes. X is seldom used as arc length. It's usually used as a length, potentially in the x direction, but not necessarily. S is the classic symbol that's used for arc length. So if you're going to have to use an arc length, I would encourage you to use ds. But it's just a length, and symbols we create. So does that make sense? So I don't care if you use dx versus ds, but in a classic discussion like this, if you want to know, it would probably be q over pi r would be equal to dq over ds, because s is the classic symbol for arc length. Does that make sense? Okay. Or maybe a little bit of sense. I'm just trying to use it. Now, I am going to jump in here to help us, because we want to replace dq with something that has to do with the size or the shape of our object. And we're there, right? We could start the assembly of our process right now. Let me show you what I mean. Let's start creating this here. I'm going to solve that for dq, and I get dq equals q over pi r ds. Is there anybody else know where pi r came from, just to make sure? We're all good then? Okay. So df is going to be the portion of this force. And right now, df would be q, that's the little charge. dq, that's the amount of charge of the blue box. K, that's our proportionality constant, divided by the separation distance, which is r squared, times the cosine of theta. That's to scale it for the amount that's just to the right. And this is going to equal df in the x direction. All good? Yes. Now, we're going to do a substitution for dq, because we can't really integrate over q like this, because we don't really know what to integrate over, what our limits would be. And it doesn't describe the geometry, so we need to integrate over the geometry of the system. That's what this was all about. So we're going to sub that in now. So d f of x equals, I want to do some algebra if you're okay. I know how to do it. So q ds k over pi r cubed cosine theta. So I put the q in the ds in the numerator and the pi and the r in the denominator. Is that okay with you guys? That's a lot for some of you to digest. So I'll wait a few seconds to make sure you know what I did. So where the dq was, in the numerator, I put q times ds. And the denominator, I put pi times r, but there was already an r squared there, and that made it r cubed. I'm just doing the algebra, but try not to make it too hard, because it's already kind of a mess. Okay, here's the problem. Every piece of arc is in a different location. So if I want to integrate over the arc length, I bet where the arc length is related to what theta is. I need to find a way to relate either theta to s or s to theta. There is a way to do it, and it's not hard. It's not much there's not much to work from here. So I'm just going to tell you, because we talked about it last year, but it's been a long time since last year. So a quick aside. If you want to go from an angular coordinate to a linear coordinate, do you remember this from last year? You just multiply by r, the radius. So the arc length is related to theta. In fact, we could say that arc length is equal to r times a piece of theta. If I sweep out a small amount of angle, that's what that is. D theta is going a small amount of angle. The amount of arc length would be how much angle we sweep out times r. So if I could just just imagine, we're going to go from here all the way to there, right? We're going to sweep theta from 0 to pi. Our little piece of arc length is over there someplace. So imagine I put a pen here, and I go, okay, move a little bit in the theta direction. That would be the size of d theta, right? That would be the piece of arc length. So that's what we're doing here. We're saying our piece of arc length is equal to a piece of angle times r. What's more valuable for us is that means we can not only point to each piece of charge, but we can point to it using theta now, right? That's what it really means. So I'm going to replace ds with r d theta. They're still arc lengths, and because it's an arc length, it still works for my function here. But what it does is it gives me everything in terms of theta. So I'm going to write this here bigger. All the things? Yeah.
Is it not DFX?
Is it not what?
Like
Oh, sorry. Does it all look good? Any questions on what I put there? Yeah.
Is d of theta just the angle where the charge is?
D of theta actually would be this. I'll draw it better because I've can't say I've done a great job with this. So let me see if I can do a better job. Theta would be what I would consider to be the start here. So like, oh my God. That's what theta is. So if I want to find where this piece is, I would say start at 0 and go out theta. That's where the start of this piece is. Then d theta represents the amount swept out inside here. This is d theta. And then we're saying that this length here and this length here are the same. They're not really, but we're saying they're the same because we're saying the bar is kind of thin. That's our ds. Does that make sense? Okay. I didn't really explain that particularly well getting to here, so I'm hoping I'm clarifying it now. How are we doing? We all doing okay? This is not easy, but I'll remind you, I told you, hardest stuff we do all year in the first month of school. You're looking at it. This is hard. This is brain busting kind of stuff. There will be stuff in the future that's like this, but when you've done this 5 or 6 times and you see the limits of what we're going to have, like you're seeing this one. Well, once you've done this problem once, you can do any version of this problem. And there are only like 3 shapes that we're all going to deal with this year. Stuff that's circular, stuff that's straight line, stuff that's flat. That's really about it. So, I want to get back to this. Inside here, remember, is Coulomb's law. But this is just the force from one little box scaled in the horizontal direction. But once we've done that, a bunch of these things stay the same for every single box. This stays the same for every box. That's the point charge. This stays the same for the box, for every single box. That's the total charge. This stays the same for every one of the boxes. This stays the same for every one of the boxes. This stays the same for every one of the boxes. And this stays the same for every one of the boxes. None of those change for any of the boxes. So let's collect them all together. So Q, K over pi r squared. I just canceled the 1r from the top and bottom. So we're just left with cosine theta d theta. Now, if you think about it for just a minute, theta starts at 0 and ends here. What's here? Right? Pi over 2. So we're going to integrate from 0 to pi over 2, and we're going to multiply that by 2. So we did not finish. Your homework